So we are here to continue our previous lesson about structural analysis. We have the same objectives for this lecture, but from last time we did the method of joints to determine forces in members of a truss. We defined the truss. We defined the external support reactions, and now we will be going about the other method which is the method of sections. So the same assumptions are still in place. All loadings are applied at the joints, and the members are joined together by smooth pins, and each truss will act as a two force member, and we will be determining if the force in each member is tension, tensile force, or compression or compressive force. So this is what our truss members should be subjected into, either in tension or in compression. So before we go to method of sections, let's continue with determining zero force members. So what are zero force members? So these are members that are included in the truss but doesn't support any load. So why are they there? Why are they still incorporated in the truss? So they are necessary for stability and should be available when additional loadings are applied to the joints of the truss. So these members can be identified by inspection. So we will be examining trusses, and we will be doing a free body diagram, and we'll be determining the rules for how to identify this zero force member. So they occur at joints where only two members are connected and no external load acts along either member. And it also occurs at joints having two collinear members. A third member will be a zero force member. Okay, so what we are looking for is either two joints with no external loading or support reaction, or three joints where two of these three joints are collinear. So let's examine some examples. So given this truss, so by analyzing and doing a free body diagram from certain joints, what we want to look for are truss joint which is not loaded and is composed of two members. So by inspection, we can say that that is joint A and joint D. So doing a free body diagram for joint A, as you can see here, so joint A will be composed of two members. So if you do there are two forces, FAF and FAB. If you do a summation forces in X, since there is all should be equal to 0, since there is only one force, FAB must equal 0. Same goes for summation forces in Y equals 0. There is only one force, FAF, so FAF must be 0. So then that is two joints two members composing a joint which is not externally loaded. So there is no external loading here or even support reactions. So by doing this summation free body diagram and equilibrium equations, we concluded that members FA and members AB are zero force members. Let's do free body diagram of joint D. So for joint D, this is the free body diagram. If you do a summation forces in Y, there is no other Y component other than the component of FDC, and FDC sine theta is equal to 0 since the sine of theta is not equal to 0. So FDC would be equal to 0 since there are no other Y components. And if you will do a summation forces in X, since you only have FDE and the X component of FDC, which is 0, therefore FDE is also 0. Okay, so those are what we are looking for: two joints that are not externally loaded or doesn't have support reaction, and that qualifies joint D and joint A. So the two members composing that joint must be zero force member. So let's define the rule. So if only two non-collinear members form a truss joint and no external load or no support reaction is applied to the joint, the two members must be ZFM or zero force members. Okay, so what you're looking for are two joints which doesn't have external loading or support reaction. Then you can conclude that those two joints, without doing the free body diagram, the summation forces that we did earlier here, you can already conclude by inspection which are zero force members. Okay, so that's the first rule. Okay, so now we have an okay, this is what the loaded members of the truss will look like. So we took out FA, member FA and member AB, as well as member DE and member DC. So that makes the, if you will use method of joints on this truss, it would be 1, 2, 3, 4, only 4 joints. So that simplifies the calculation if you can identify the zero force member by just inspection. So that's first rule. Okay, now we have another truss in here, and what we are looking for on the next condition is a joint which is composed of three members, two of which are collinear. So if you will analyze this, which one will qualify as such a joint? Again, no external loading. So joint E, can you use our rule 1 to identify which are zero force members? No, because joint E is composed of two joints, but there is an external load. So forget about the first rule since there is an external loading. Okay, what about joint D? So if you do a free body diagram of joint D, since FDE and FDC are collinear, the summation forces in the X in here, we are shifting axis, okay? So please don't be confused. So this is the y-axis, this is the x-axis. They are always perpendicular to each other. So if you do summation forces X, you only have one force, that's FDA. If you do summation forces Y, you can conclude that FDE and FDC are equal. So we have a joint composed of three members, two of which are collinear. The third one is a ZFM, zero force member. What else? Okay, joint C. What happened to joint C? Joint C is also can be defined as such a joint that what we are looking for. So composed of three members, two of which are collinear. So if you do summation forces in X, FCA sin theta is equal to 0. FCA would be equal to 0 since there are no other y components, and since sin theta is not equal to 0. And if you do a summation forces in Y, you will find out that FCB is equal to FCD. So member CA and member DA here are zero force members. Okay, so this is the second rule. So if three members form a truss joint for which two of the members are collinear, the third member is a ZFM provided no external force or support reaction. Okay, so for both rules, what you're looking for is the joint should have no external force or have no support reactions. So what the joints where it is pin connected or roller connected or rocker connected or whatever connection occurs, forget about your analysis. Okay, so no external force or support reaction as a component that acts along this member. So this is what the previous truss that we analyzed look like. So we removed member DA and member DC. So if you will do method of joints here, you only need to do 3 joints. Okay, that simplifies the calculation. So another rule, the third one, it's almost coinciding with the second one. So if a joint only has 2 members and they have a load, if the line of action of the resultant force or the load from the applied loads at the joint is collinear with one of the members, then the other member is a zero force member. It's like a special case of the second rule, where the external load will act as one member. Okay, so what you're looking for is there are 2 joints. The external load is collinear to one of the 2 joints. Therefore, the other joints which is not collinear with the load is a zero force member. Okay, so let's look at another example. So we are to determine all the zero force members of the truss shown here, this one. So it has 8 joints. So if you want to do method of joints here, you need to do 8 joints. But first, you need to identify which are zero force to simplify your calculation. Okay, so what qualifies with our rules? So you can look at the joint at the middle, which is joint G. What's in joint G? You have 1, 2, and 3 members, and 2 are collinear. The third one must be a zero force member. That happens to be member GC. Okay, so that's 1. The next candidate would be joint C is composed of 1, 2, 3, 4, 5, 6 forces. So it's not in the criteria. We are only looking for 2 or 3. Joint D. Joint D will have the same conditions as joint G. So this is the free body diagram for joint D. You can see that 3 members, 2 are collinear. The third one, which is member DF, must be zero force member. Okay, now that we conclude that DF is zero force, if we do a free body diagram of joint F, so if DF is zero force, then F looks like a joint where there are only 3 members and 2 are collinear. So the third one, which happens to be member CF, is a zero force member. So what happens? I just want to give attention to joint B. Imagine if there is no external load, 2 kN. What will happen to member BH? It will become a zero force member. So let's say in your design, you want to cut some costs. So you don't want to put member BH. And then suddenly there is an unanticipated 2 kN load that occur. Maybe there is a cat or a dog that went up your roof. So this is your roof truss. Then you have a 2 kN load there. So if you don't put member BH, then there is nothing that will compensate for the external load. So that is the purpose of your zero force member. If there is maybe a shock load or an anticipated load occurs in your design, it will compensate for that. Okay, so not because they are just zero force member you can omit them. No, they are there for stability. Okay, so since you have a 2 kN load here, there is no zero force member analysis there in joint B. If you remove the load, you can freely say that BH is a zero force member, but since there is an external load, you can't do that. So are there still others? No. So what we have is this joint, this member, and this other member are all zero force members. But please, in your design, as you are architects, please don't remove this. Don't remove these members. Okay, so that is for zero force members. Now let's go to the method of sections. So the method of sections is almost the same with the method of joints. It says that if the truss is in equilibrium, then any segment of the truss is also in equilibrium. Just to recall, the method of joints says that if the truss is in equilibrium, then every joint is in equilibrium. So for method of sections, every segment or any section should also be equilibrium. That is, you can apply equilibrium equations. So the internal forces in the members when cut will become external forces when the free body diagram is drawn. So this is what will happen. So if you have this member acted upon by a tensile force, this is just an imaginary plane that you pass through the member, and that's what we call cutting the member. Not literally, but just passing a plane through it and doing the analysis. If you plus a plane here and you divide it into sections, this is what it will look like. So the internal forces here will become external forces. So they will act like external load to your segmented truss. So for compression, it goes the same. That would be the direction. So this is still the manifestation of Newton's law of action and reaction, which says that every action should have an equal and collinear and opposite direction reaction. So this is what the method of sections will look like. So look at this truss here. We have 1, 2, 3, 4, 5, 6, 7 joints. If you are to analyze this truss, and the required in the problem is a member somewhere in between, you have to go through some other joints before you can determine the value of the force in the truss, in the member. But applying the method of sections, you can pass a plane anywhere in the truss and do your equilibrium equations to solve the value of the force in these members. So that simplifies more the calculation. That's why we taught method of joints first before method of sections. So what is the difference between method of joints and method of sections? So method of joints, you will look here in our example, we divided the truss in segments. So if you are looking for either force BC, force GC, force GF, here you don't have to do the analysis of joint A or joint B until you reach FBC, or you don't need to do analysis of joint C, joint D, joint E, or wherever to reach this middle members. So this is what your rigid body will look like. So now here you can do your equilibrium equations. And again, the difference is that for method of joints, you are only doing summation forces in X and summation forces in Y, since they are concurrent force system. But here, you also need to do summation moments, right? Since you are dealing with not joints anymore, sections with measurements here, 2 meters, here 2 meters and 2 meters here. Okay, so we just have to do additional line in our calculation, which is the summation moments. So here, how to determine the correct sense of an unknown member force. We did this from our previous lesson when we are assuming the direction of the support reactions, and of course identifying how many support reactions there are for particular types of supports and connections. Again, you need to do summation forces in X and summation forces in Y must be equal to 0, as well as moment equilibrium. Summation moments should be equal to 0. So there is some trick here that is stated. Do summation of moments at the joint where two unknown forces pass. Again, it's better to choose your pivot point where you can cancel a lot of forces. So in this example, it is good to do summation moments about point C or point G, since you can cancel a lot of forces. For point G, you can cancel EX, you can cancel GF and GC. So that shortens your equation. So it's just a tip for you to save time and save space on your paper. So if two forces are parallel, do summation forces X or Y at the perpendicular axis to this forces. So those are just some tips in order to do our calculation faster and simpler. Okay, so now let's do an example. We have here a bridge truss, pin connected at A, and I think this is roller connected at D. So what we are asked is to determine the forces at GE, GC, and BC. You can easily do it by method of sections. Method of joints, but our lesson now is method of section. So we pass a plane AA, the middle of the truss, and we determine always the first step is to determine external reactions. So what would be the reactions here? So this is a hinge connection. What do we have? We will have two reactions, AX and AY. For the pin connection, you only have for the roller connection, you only have one reaction, and that is the normal, which is dy. Okay, so this is the free body diagram of the whole truss. So the next step should be determining the values of this external forces. So like what we are always doing, we will be doing a systematic computation for this. The first step would be to identify the given, and that includes drawing the free body diagram of the problem. So as you can see here, this is the same truss free from its surroundings, and where all the external forces are identified. So we have here an external force 100 Newton horizontal at joint E. At joint C, there is a vertical force 1200 Newton, maybe a load, and it is roller connected at D, so there is one support reaction, let's call it dy, and at joint A, it's hinge connection or pin connected, so there are two That's AY and AX. Again, we need to verify if our assumptions for the directions of these unknown support reactions are correct. So if we will do in our mind summation moments in A, let's hold A here, let's hold it right here, and identify the moments. So the force 1200 newtons will turn it clockwise, the force 400 newtons will also turn it clockwise. So it just makes sense that you make the reaction at dy to be going up, so that the moment at A will turn it counterclockwise to oppose the two clockwise moments. So for the direction of AX, if we do a summation forces X, we can see that E is going to the positive X. AX, there are no other X forces, should go the opposite direction. So that is correct. So for AY, this will remain to be an assumption, since if we do summation moments, it doesn't make sense to do it, right? So you really can't conclude. So let's keep that as an assumption. If it becomes negative, then we'll just reverse our assumption. Okay, so that is our given. This is the truss that we'll be analyzing. So identifying the required. So the required is what is the force in member GE, as well as the nature of this force, if it's tension or compression. What is the force in member GC? What is the force in member BC as well? So we will be doing method of sections, but we first need to identify the external support reactions. So that is the first step. No, that is the second step actually. First step is to properly draw the free body diagram and assume the directions of the external support reactions, and the second step will be to identify these support reactions. So for now, we will not be doing method of sections yet. That will be on the second part of the solution. So for the whole truss, let's apply our equilibrium equations. So for summation forces in X should be equal to 0, since there are only two forces, then 0, let me write here, 0 must be equal to a 400 Newton positive force minus AX. Therefore, AX is 400 newtons. So we already easily get the value for the reaction in joint A, the horizontal reaction, which is also a 400 Newton force. Next is if we do a summation forces in Y, will we accomplish anything? Not yet, since we have two unknowns, we have AY and DY. So what's best is to do a summation moments. So summation moments, and what is our criteria for the selection? Which joint are we doing? At the joint where we can cancel more forces, and that occurs at joint A. You can cancel two forces already. That simplifies your equation. So summation moments along A, so we are dealing with 1, 2, and 3 forces only. Okay, so summation moments at A must be equal to 0, so that's 0 equals, let's put the assumption here. The assumption would be the counterclockwise moments are positive, so we are looking for counterclockwise moments first for our equation. So 0 is equal to, which are counterclockwise moments? That is the force dy, right? That is counterclockwise. So let's write down that first. Again, it doesn't matter if you want to do the clockwise first, just put the negative sign. So for me, I prefer to write in the equation the positive values. Okay, so that is the moment arm is 8 meters plus 4 meters. That would be 12 times dy. That is the moment made by force dy. And the other two forces are clockwise, so they are negative. So we have minus, this is this 400 newtons times 3 meters. So that's 400 times 3, that's 1200 newton meter. So let's just write it directly. The next would be, this would be 1200 times 8 meters. So that would be 2 times 8, that's 9000. That's also negative, that's 9600 newton meters as well. So if we will manipulate this equation, we can find that dy would just be equal to, transpose the negative values on the other side, it will become positive. So that's 96 plus 12 divided by 12. And we will find the reaction dy as 900 newtons. So it's a positive, so it means that our assumption is correct. Okay, now that we have a value for dy, if we do a summation forces in the y direction, I'm not writing the assumptions for x and y since we are operating on the sign convention of the Cartesian coordinate plane, where x going right is positive, y going up is positive. Okay, so summation forces y must be equal to 0. So we have three forces. We have dy going up, so 0 is equal to dy, or 900 newtons going up, that's positive. We have ay, that's also going up according to our assumption. And we have a force 1200 newtons going down. And that's all our y components. So if we will do the math, that will give us 1200 minus 900 should be equal to ay, and that is a positive value. So it means that our assumption for the direction of ay is correct. So we have ay, that's 300 newtons. Okay, now that we properly identified, these are still not what is asked in the problem. This is what we are looking for, GE, GC, and BC. These are just the external reactions. So our problem will have a second part for the solution, and that is where we do the method of section. So now we cut our truss, where we can analyze the forces that are recorded in the problem. So that's GGCBC. So it's just logical that we cut our truss this way right here. If we cut it horizontal, we cannot take account for GE, so that will lengthen our solution. So it's better to cut your truss where all the forces asked in the problem are will be addressed or will be exposed. Okay, so it's better to do this cut right here, this red line here. And the next step is to choose which segment are you going to apply your equilibrium equations. We can say that we have the left segment or the left section and the right section in here. So what do you prefer? So it doesn't matter actually. You can do your method of sections in either section, but then again, what you want is to save time and have fewer forces to deal with. If you look at this segment, in the right segment right here, how many forces are you dealing with? You're dealing with 1, 2, and 3 forces, as well as the additional 3 forces that are required. But if you look on the left one, you are only dealing with 2 forces. So I think the better choice is to do the left segment or the left section. But again, it doesn't it's okay. You will also arrive at the same answer if you select right the right segment. But for this example, let's do the easier one, which is the left segment. So now that we identified AX as 400 newtons and AY as 300 newtons, we can do another free body diagram for our selected segment. Okay, so the continuation of the solution is right here. So the free body diagram, okay, AX is 400, AY is 300 newtons, and these are the correct directions. And you can see here, since we cut our truss, we expose the internal forces as external forces. So we have FGE, FGC, and FBC, the things that we are actually looking for, right? So please recognize here that the slope of member GC is like a 3, 4, and 5 triangle. So you have a 3 height here, you have a 4 here, and the hypotenuse is 5. Okay, so that simplifies our that will simplify our analysis. Okay, so what we want to know is apply equations of equilibrium that will give us the values of FGE, FGC, and FBC. And since we are doing method of sections, as I mentioned before, that our equilibrium equations compared to method of joints, which is only Fx and Fy, here we can also use summation of moments, and we will select the joints where we can find unknowns. Okay, so which joint should we do where we can find unknowns? So let's analyze joint A. So for joint A, we cancel these two forces, yet we have 1, 2, 3 unknowns. So it's not a good idea to do a moments in joint A at this point. Let's go at joint G. If we do a moment summation in joint G, let me write that down. So if we do a summation moments in joint G, where the assumption is still anticlockwise is positive, that's equal to 0. We can cancel GE at the moment. We can cancel FGC since they are concurrent with point G. We have two knowns here in 400 newtons and 300 newtons, and we have one unknown in FBC. So we can find FBC by doing a moment summation about point G. So let's do it. So 0 would be equal to, so we're doing some summation of moments at here at point G. So what do we have? Anticlockwise moment would be, we have here this 400 newtons right here, right, times 3 meters, that would be 1200 Newton meter. Another anticlockwise moment. Okay, I hope you can see that it's turning it. No, it's actually clockwise. Sorry. So that's negative. Okay, so please be very careful in your analysis. So if you hold point G and you pull with 400 newtons, it will turn G clockwise. So it's negative. So what about this 300 Newton force here? It will also turn it anticlockwise. So sorry, we wrote the negative values first. As I mentioned earlier, I prefer to write the positive ones, but then again, it doesn't matter as long as you stick to your sign convention properly. So this is also another 300 newtons times 4, that would still be minus 1200 Newton meter. And the last one would be an anticlockwise force that would be positive, that is plus, this is FBC, this force right here, times the moment arm, which is 3 meters. So that's 3 times FBC. Okay, so manipulating this equation right here, that would be 1200, both negative transposed to the other side becomes positive. That's 2400 Newton meters divided by 3. So you get the value for FBC to be, is it positive? Yep, it's a positive value. FBC 24 divided by 3, that's 800 newtons, and it's okay, I haven't discussed the sign convention for sorry, the assumptions for this this one. But again, if you do summation moments at G, two forces would be clockwise, so it just makes sense that FBC must turn G anti-clockwise. So, and we found out in our calculation that this assumption is correct, that the direction of BC is such. So what does it mean? Force BC is as you can see is pulling apart this is pulling this member, so it's a tensile force. Okay, so it tends to elongate the member according to this cross-section cut. Okay, FBC as 800 Newton, that is a tensile force. Okay, now that we have a value for FBC, can we do what can we do? We can do summation forces X. Not yet, since there is an unknown component of FGC which is in X. That's 4/5 of FGC and FGE. So we cannot do summation forces yet. Let's do another summation moments and choose which part are we going to do the summation moments. So let's say point C. We can do summation moments at point C. Since FGC and FBC is going through it, we can cancel that. We have known values for the reactions, and we have one unknown, which is FGE. So it's good to do summation moments at C. Still, the assumption remains to be anticlockwise as positive equals 0. Okay, now is the assumption for the direction of G correct? If we will do summation moments at C, the 300 newtons will turn it clockwise, and there is no other. This 400 newton force is also concurrent with point C, so it will not make a moment about point C. The other one, the force FGE, should counter that clockwise moment, and it should be counterclockwise. So we can say that the assumption for the direction of FGE is realistic and correct. So summation moments here, that would be 0 equals, the first one would be the anticlockwise moments. What is the moment arm? The moment arm is 3 meters, so that's 3 meters times FGE. That should be equal to 0 if you minus the moment that is produced by the 300 newton force, which is for the moment arm is 4 meters plus 4 meters, that's 8 times 300 newtons, that would be 2400. So it looks like FGE would have the same value as FBC, 2400 newton meter. So what's left? Manipulate this equation, transpose the negative 2400 on the left side, and FGE 2400 divided by 3, that would be 800 newtons. And it's positive, so it means that our assumption is correct. So that's 800 newtons. And what is FGE doing? It's compressing joint G. So it's a compressive force. Compression. Okay, so now we have two knowns. Only one force is remaining, and that is FGC. So FGC, what do we have in FGC? We can actually do either a summation forces X or a summation forces Y. So let's do a summation forces Y, since there are only two forces involved, the Y component of FGC and the 300 Newton force here. So let's do that, and right here summation forces in the Y direction. So what are the components we have here? This is 0 equals 300 newtons, that's going up, so that's positive. And what remains is the Y component of FGC, which is, that's 3/5 of FGC, and that is going down, so minus. So the assumption for FGC went like this, since you have only one force going up in the Y direction, so the other force must be going down. That's why the direction of FGC is assumed to be going towards C. Okay, so what happens here is, again, that is 3/5. So 3/5. So we will not be solving for the angle, we'll just do the proportions, FGC. So if we'll do the manipulation for this one, FGC would be we transpose this 3/5 FGC on the left side, that would become positive. You divide 300 by 3 and multiply it by 5, that's 100 times 5. So this means it's 500 newtons. And what is FGC doing? It's pulling this member GC. So it's a tensile force. Okay, so that is, we already found the required from our problem, that is the forces, and this is by doing method of sections. So if you do method of joints, that will take some of your time, and here's another method to make your calculations simpler. So I hope that you followed that. So it all starts with drawing the correct free body diagram, and then properly identifying how many support reactions there are, and calculating the support reactions, and cutting your truss into segment, and applying your equilibrium equations. So since there are a number of joints, it should be according to your analysis, where you will do the summation moments, where you can develop equations with one unknown. That unknown should be what is asked in the problem. So that is what we see here, how we select the pivot points, which is point G, joint G, and joint C. And as your unknowns are gets values, you can shift to doing force summation as long as your unknowns is limited to 1. Okay, so that is how you do your method of sections. Let's do another example. So let's have this truss, and what we are asked to do is to determine the force in member EB of this truss, of this roof truss, loaded as such. As you can see, the external loads are here. They all have values, as well as the reactions at joint A and joint C. So you have 4,000 newtons and 2,000 newtons, so there's no need to compute external reactions. So again, indicate whether the member is in tension or compression. So actually we have a hint here where we must do the section or the cutting of the cross section. We have here plane AA cut here and plane B. So if we will take the cross section of AA on the left side, it will look like this. Okay, so this is your free body diagram of your cross section. So what forces are exposed? We exposed force ED, force EB, FFB, and FAB. And what we are looking for is FEB, force in member EB. Only one, this one here. So let's see if we can do this in one go, and which part we need to do the summation moments. Alright, so this is the given for this problem, the same cross section that we have revealed earlier, and the required is FEB. So the solution, let's do a summation moments along B, since it will eliminate a lot of unknowns. FEB, FFB, FEB. Unfortunately, we are looking for FEB, but we need to find we need to do another step and find a value for unknowns such as FED, and we will do another sectioning, which is something similar to method of joints. Okay, so this is like method of sections and method of joints all together. Okay, so let's do summation moments in B must be equal to 0. So what are the moments? Positive moments are considered as the counterclockwise moments. So doing the math, that would be 0 is equal to, so about point B, what are the counterclockwise moments? About point B, you have here a 3,000 Newton force times 2 meters. That's counterclockwise, right? Right there. So that's 3,000 times 2, that's 6,000 Newton meter. That's this one. We also have a counterclockwise moment from 1,000 newtons times 2 plus 2, that's 4 meters, so that's 4,000, so that's plus 4,000 Newton meter. And we also have this 4,000 Newton here, which will turn B clockwise, so it's minus. So it's minus, this is 4,000 times 2 plus 2, that's 4 times, that's 16,000 newtons. So let me write it here as 16. Okay, let's write 16,000, not 16 kilonewtons. 16,000 newton meter. Okay, this force is accounted for, this force is accounted for, this one is accounted for. What else? We have FED. So for FED, we will apply the principle of transmissibility of the vector. We either slide it at point E and resolve it into components, or at point C. So it's easier to slide it at point C and resolve it into components. So this will have a component, since this is 30 degrees, this is adjacent, so this is FED cosine 30, and that force is concurrent with point B, so it doesn't make a moment. The one that makes a moment is the y component, which is FED. Take note, we're just calculating for FED since we're going to use it later for another section. And the component is opposite 30 degrees, so that's sine 30. Okay, so FED cosine 30 will not do any moment since it's going to pass through point B. And FED will do a counterclockwise moment. It's going like that. Okay, so it's doing a counterclockwise moment, so it's positive, so that's plus FED sine 30 times 4. So FED sine 30 is 1/2, so that's 2 times FED. Sine 30 times 4 is 2. Okay, so manipulating this equation, we just need to transpose all the known values on the other side. That would be positive 16,000 minus 6,000 minus 4,000. That would be 6,000 Newton meters divided by 2. So the value for FED would be 16 minus 6, that's 10 minus 4, that's 6 divided by 2, that's 3,000. Okay, 3,000 newtons, and it's positive, so it means that assumption here, it's compressing point E, so it's a compressive force. Okay, so that's not what we're looking for. We're actually looking for FEB. So why did we solve for FED? Next is, if you can see that there is a hint here where you will do the sectioning, we need to pass another plane BB to isolate joint E. So it looks like it will become a method of joints. So in method of joints, you're only involving summation forces X and Y. Okay, we previously solved that FED is 3,000 newtons and its compression towards point E. So this is our solution now. This is our unknown right here. This is also another unknown, but what we can do is we can do a summation forces along X. Okay, let's do a summation forces in X. So summation forces in X equals 0. So we only have the X component of FED and the X component of FEF. So that's 0 equals, the positive one is the component of FEF, that is cosine this component right here. Let me draw it, that one. And this is the component of FED. And this component is adjacent to 30, so that's cosine. So that's FEF cosine 30. minus, this is also a cosine 30, FED this time. So that's 3,000 newtons cosine 30. As you can see, we both have cosine 30. So we can cancel that out and we can conclude that FEF is just equal to 3,000 newtons also. So FEF equals 3,000. And it's also compressing joint E, so it's compressive force. Okay. So what's next? What remains is to do a summation forces in Y direction. Since we already have a value for FEF and FED, and we have 1000 newtons here and one unknown FEB, so let's equate it to 0. So what are the Y components? The Y components going up are the components of FEF and FED, which are both sine. So that's 3,000 sine 30. So that's 3,000 newtons times sine 30. 30 degrees. That's 1/2. Plus another 3,000 newtons sine 30. 1/2. That means this will just become 3,000 newtons. That's twice the halves of 3,000 newtons. So that's 3,000 newtons only. What's going down? We have another 1,000 newton going down. And the value for FEB is also going down. So FEB, and this is the required in the problem. So since we only have one unknown, we can manipulate this equation and solve for FEB. So the value of FEB would just be FEB, we transpose it on the other side, and this would become 3,000 newtons, 1/2, 1/5 plus 3,000 newtons, 1/2, 1/5, that's 3,000 minus 1,000, that will become 2,000 newtons, and it's positive, so it means that the assumption for the direction of FEB is correct, and it tends to elongate point E, so it becomes a tensile force. So that is what is required in the problem. So segment 4, let's write it down. The solution, the answer is FEB now we have solved the problem. It's equal to 2,000 newtons or 2 kilonewtons and is a tensile force. So that is how you do your method of sections, and sometimes you should do both. So you need to learn both method of sections and method of joints. So it's a tensile force. Okay, so that is our answer for this problem. So this lesson is can still be found from our resource book, Engineering Mechanics Statics 4th edition by Russell Hibbler, and this is pages 282 to 296, just continuation of our lesson, our past lesson, still structural analysis. So as always, thank you for your attention, and if you have any clarification, use our Q&A link, and if you want, you can also review other examples and do the other fundamental problems for that chapter in our reference book. So thank you and good luck.